Good evening, everyone. Welcome to today's problem solving section, week 6, course Digital Electronic Circuits. So we will start with magnitude comparison. So say we want to compare two numbers, say A and B. Can we use subtractor for comparison? So if both A and B are equal, then if what will be the output for A minus B? It will be equal to A minus A, say it will be 0. And if A minus B we are performing and A is greater than B, then this value is greater than this value, so number will be positive. And if we have A less than B, then this value will be smaller than this value, then the final will be A minus B will be negative number. So with this, can we use subtractor as a comparator? So yes, we can use a subtractor as a comparator with some combinational logic. So if we consider, say, a 4-bit subtractor, and let's consider 2's complement based subtractor, then final output we will have the subtracted result, which will be 4 bits, and one borrow output. Say borrow output. So we need, let me denote this as Cout. We need a combinational logic such that which can deduct whether it is a 0 or whether it is a positive number or whether it is a negative number, and the final output will be whether A is greater than Y or whether A is equal to Y or whether uh, X is less than Y. So we have inputs as X and Y, so let's take an X and Y. These are 4-bit inputs. So we are performing X minus Y. Then now if X is equal to Y, we have already seen the 2's complement based subtraction. So when we subtract, okay, I'm taking X minus Y itself, then we say that there is a carry when the number is positive. So see, there is carry C out. And if the number is negative, then the carry is 0 and we will take the 2's complement. That the result is in 2's complement form. So with this, can we come for a condition for X equal to Y? At this time, we want C out to be 1 and we want S3, S2, S1, S0 all to be 0. So we have S3 bar, S2 complement, S1 complement, S0 complement. Because we have two conditions, one C out is 1. So the next condition for this. So when X is greater than Y, that time C out is 1 and any of S is 1. So S3 or S2 or S1 or S0. And when it is less, we have no carry. So we have no carry option. So this is the combination logic which will give the comparator results by using the subtractor results. So next, 1-bit magnitude comparator. Now instead of using a subtractor, let's write the truth table for a comparator. So we have say two numbers. These are 1-bit numbers, and the output, this will be the input to the comparator, and the output of the comparator is x is greater than y, whether x is equal to y or x is less than y. So we have three outputs, and with this we have four combinations. Let's try this. So here first 0 0, x is not greater than y. Here x is less than y. Here yes, x is greater than y. And 1 1 also, this output will be 0. Equal to, it is equal 1 0 0 or 1 1, and other two outputs will be 0. For less than, this output will be 1 and other outputs will be 0. So with this we can write the equations for x greater than y. Say I am denoting g for greater, x y complement, and x equal to y is the equal to condition, x complement y complement plus xy, and x less than y less than x complements y. So this is the 1-bit comparator. So we got some equations for greater, equal and less. So with this, now let's try the 2-bit comparator. So before that, let's implement this. So x bar y bar plus xy. This is the XNOR operation. So we can also convert it as x y bar plus x bar y. This is XOR's complement. So with this we can also implement x y bar x y x bar y x equal to y. This is x greater than y. This is x less than y. Okay. So now with this we will go to 2-bit comparator. So consider x to be 2 bits. So x1, x0, and y also to be 2-bit number, y1, y0. So already we have seen from the 1-bit comparison, if I compare G0 alone greater than, so it is x0, y0, and E0, it is not XNOR operation, and L0, it is x0 bar y0. So the same way we can write for G1 also. We are comparing bit by bit first. So with this, if x is greater than y, then either the MSB bit, if we consider x1 as the MSB, if MSB is greater, then x is greater. Else, MSB are equal and LSB bit is greater. So these are the two conditions in which we can say x is greater than y. So with this, this is greater of G1 plus here it is equal. X1 and Y1 are equal. So E1 and with this is condition for G0. So in this way we can obtain the equations from this G0, E0, L0. So the same way for x equal to y condition, the first condition is x1 should be equal to y1 and at the same time x0 should also be equal to y0. So for this, how can we write? So we want E1 to be true as well as E0 also to be true. And the next x less than y. So x1 should be less than y1 and x1 should be equal to y1 and x0 is, so here for this the MSB should be less, then the number will be less, else MSB should be equal and the LSB is lesser. So in this condition x less than y is L1 plus E1 and L0. Any doubts? Next, for the n bit comparison, also in the similar way we can write, if we consider the n bit number x to be xn minus 1, xn minus 2 till x1, x0 and yn minus 1, yn minus 2, y1, y0. So condition for x greater than 0 will be either this MSV is greater or the previous MSB should be equal and then the next bit should be greater, or the previous two bits should be equal and the next bit is greater, or previous bits down from MSB down till E1 are equal and the last bit is greater. The same way we are extending the same 2-bit formula for n bits. E1 is F. And similarly for greater than, less than. So the last, the MSB is itself less, or it is equal, the next bit is less. So you can see instead of greater, now we have to check the condition whether it is lesser. So n minus 2 G, instead of G now it is L n minus 3 plus all the bits from MSB down till E1 are equal and L0. Okay, so with this we will solve one question. If x1, x0 and y1, y0 be two unsigned 2-bit numbers, function f is 1 if x is less than y and f is 0 otherwise. The minimized SOP of product sum of product SOP form for f is. We have already seen the equations. Can you try this question? Say I have a 2-bit comparator and the inputs will be 2-bit input x1, x0, y1, y0. The output will be x less than y, x equal to y and x greater than y. So they have said this is our f. So f equal to 1 when it is lesser. So we want to evaluate this function. So the function x less than y is, we have seen, either the MSB is 1 less or it is equal and LSB is lesser. So here two bits. So L0 will be the LSB and L1 has MSB if we consider. So with this we know the equation for L1. It is lesser. So x1 bar y1 plus E1 x1 y1 x1 bar y1 plus x1 y1 and L0 it is x0 bar y0. So this is x1 bar y1 plus, I will multiply this inside, x1 bar x0 bar y1 bar y0 plus x1 x0 bar y1 y0. So this is the expression. Now we will get the minimized expression. So I will use K-map. Any answers for this question? So I have x1 x0 y1 y0 0 0 0 1 1 1 1 0 0 0 1 1 1 0. So the first is x1 complement y1. So x1 is complement in these two rows and y1. Y is 1 here, here, here and here. Then next this one x1 bar x0 bar. So x1 bar x0 bar y1 bar y0. So this next is x1 and x0 is 0. So in this row, the last row, when y1 and y0 are both 1. So this one. And the other will be 0. Now we can simplify this. Okay. So this we form a quad and we can form one pair here and one here. Okay. So now let's write the equation. X less than y equal to this quad. Here x1 bar is not changing and here y1 is not changing plus this pair x1 bar x0 bar and y0 plus this pair x0 bar y1 y0. So this is the expression. So it is x1 complement y1 plus x1 x0 complement y x0 y1 y0. So answer is C. Any doubts in this question? I am audible, right? My screen is also visible. I am audible, right? Any doubts? So, if this question is clear, okay. Next question we will go. Try. The output of the 3-bit comparator is logic 1. Whenever the 3-bit input A is greater than 3-bit input B. The number of combinations for which the output is 1 is, so they have given 3-bit input. So A 2 down to 0. See, this is greater than B 2 down to 0. So the number of bits, total number of bits is 3 plus 3. So total we have 6 bits. So total 2 to the power 6 combinations or entries in the truth table we will get. So total 64 combinations we will get. And total 2 to the power, like for one input it will be 2 to the power 3, which is 8. So for this many combinations the equal will be 1. So this results will be equal. So total 64 minus 8. Total 56 combinations will be either less or greater. So it will be both half. So 56 by 2, it is 28 will be greater. Plus another 28 will be lesser. The answer is 28. So this you can also write it as 2 to the power 6 minus 2 to the power 3 divided by 2. So if for example I take 1-bit example and show you that A and B 0 0 0 1 1 0 1 1 equal, greater and lesser. These are the conditions when it is equal, and this is greater and this is lesser. So here you can see, just for one example, I have total number of bits as 2 to the power 2 minus, for 1 bit it is 2 to the power 1 divided by 2. So I will get 1. So only for one combination it will be either greater, plus one combination it will be lesser, and this number of bits like 2 to the power 2. So here if I want to split it, 2 to the power 1 will have equal, plus 1 lesser, 1 greater. So you can say this is how we speak. So with 1 bit you will have 2 combinations. So for the 2 combinations you will have equal to, and out of the rest of the 2, half will be greater, half will be lesser, and with that, and total number of combinations for 1 plus 1 2 bits, so total 4 combinations. So with that the correct answer is option B. Next we will go for weighted codes. Let's say our binary coding, we have weights of 8 4 to 1, because we write 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So these are weighted codes. So if, for example, if we consider 1010, what is the value? It is 1 into 2 to the power 3, which is 8, plus 0 into 2 to the power 2, 4, plus is 1 into 2 to the power 1, which is 2, plus 0 into 1. So the value is 8 plus 2, 10. So 8421 is the weight, and this is associated with the position. This is based on position value. So for example, we can have other weighted codes. For example, say 2421. So this code, if we take this example, then it can be 1 into 2 plus 0 into 4 plus 1 into 2 plus 0 into 1. So something like this. So these are the weighted codes. We have something called as gray code. So in the binary, let me take a 4-bit number B3, B2, B1, B0. Then let me take some few binary values here. So this is binary count of 3, binary 4. Okay. So if we see here, there is a 2-digit change. And if we consider this, here there is a 3-digit change. So as it is explained in the class, if we consider conveyor belt and it is moving from 1 to 2, so this this should be changed to 0 1 0. If initially 1 bit it is changing this 1 to 0, and then it is changing to 0 1 0. In this way it will be like it is moving in reverse direction because it's like this. So in this way there can be an error when we have 2-bit change or 3-bit change. So we want a code which will have 1-bit change. So this possibility of a decoding error will be there in this binary. So we go for gray code. Gray code is an unweighted code, and it with unit distance. That is only one position difference will be there in terms. Only one position change will be there between the two successive numbers. So one method, how can we obtain this gray code? So one of the method is based on reflection. So we also call it as reflected code. So let's see. If we have 1-bit number, I can divide this so that I can make the code. Say I have 0, then its reflection will be 1. Now if I have two numbers, 2-bit numbers, so it will be 0 1, and there will be reflection 0 1, and before the reflection it will be 0 1 1. So is this reflection code correct? Is this a reflection? Reflection is this 1 should come here, then this 0 should come here. So now if you see from this to this, only 1 bit change is there, and from this to this, only this bit change is there, and from this to this bit change is there. So we have only 1 bit change. Now if we go for 3-bit numbers, so 00, 01, 10. This we will repeat it 1110 and top everything like now reflection 10, 11, 01, 00. Now above the reflection it will be 0 and below the reflection it will be 1. Any doubts? Any question? So now if we try for 4-bit, then this complete 3-bit will come here. 3, 001, 011, 010, 110, 111, 101, 100. And now the reflection of it. This here, then 111, then 010, 011, 001, 000. And above the reflection, 0, and below the reflection, 1. Any questions? Okay, so here also you can see there is a 1-bit change here. So every successive number there is 1-bit change. Okay, so in this way we can obtain the gray code. Next we will see conversion. How can we convert a binary number to a gray code? So we have a formula for the nth bit will gray and will nth bit of the gray code will be the nth bit of the binary, and ith bit of the gray code will be its previous bit XORed with bi. So for I is less than n. So if we draw the logic circuit or the gate level implementation V3, this is our MSB bit, will be our G3. Then the previous bit XORed with the B2 to give G2. Then previous bit XORed to with the B1 to give G1. And previous bit XORed with B0, we obtain, okay, why this is G3, G2, G1, G0. So in this way we can convert. This is our LSB bit. Any binary number to gray code. So the similar way, if you want to convert gray code to binary, then similarly the nth bit of binary is nothing but our nth bit of the gray code, and the bi is bi plus 1 XORed with gi here instead of bi, or I is than. So the first G3, if we consider 4 bits, will be B3, and this will be XORed with this one B3 and G2 to give B2. So here you can see. Next, XOR, we will take B2. Instead of previous input, now we are taking from this output, and then G1, B1, and this one, B1 with G0, B0. So this is our gray code to binary conversion. So with this, we will go to the next question. Which of the following represents the gray code of A to E16? So this is the implementation, like we have to use convert binary to gray code. So let me write this in the binary value. A is 10 and E is 14. Our binary code is 8421 code. So 10 is represented as 010 and 2 is 0010, and then E14 8420. So this is the code. Then next, the first bit will be same. The next bit will be first bit will be same. Next bit will be the previous one XORed with 0, and this 2. Then this 2, this 2. So the next will be 0 XORed with 1, and the next bit will be 1 XORed with 0. The next will be this and this, 0 XOR 0. Then this 2, 0 XOR 0. Then this 2, then this 2. Okay, so now with this, we will start writing this 2. This 1. 0 XOR 1, 1. 1 XOR 0, again 1. 0 XOR 0, 0. 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 0, 1. Then next these 2. 1, 1, 1, 0. 1, 1, 0, 1, 0, 1. So this is our gray code. So now what we have the gray code as 1, 4, 1, 0, 5, 1, 0, 7, 5. This is F, this is 3, and this is 8, 5, 2, 1, 9. So this is our 16 hexadecimal number. That is option B. Clear any doubts? We will go to the next question. Next topic, Hamming distance and parity code. So the number of bit position by which a code word differs is called as the Hamming distance. Number of bit position by which code word differs is called as Hamming distance, and we use bitwise XOR and count the number of ones. So it can be found by counting the number of ones in the bitwise XOR of the two codes. This, so the parity code, that is data with a parity bit, can detect one bit error. So if we have say a data 1 1 0 1. So if we are using even parity, then the code word will be the first bit will be the parity bit. So it's already even number. So 0 will be the parity bit and the data. Similarly, if the data 2 is 1 1 0 0 0 1, the code word will be 1 because there are 5 ones. So 1 and the data. So this parity code can detect one bit error. And just we have some general formulas. So to detect B bit errors, minimum Hamming distance d min should be equal to B plus 1. And to correct B bit errors, minimum Hamming distance d min should be 2B plus 1. So if, for example, if you want to correct a 1 bit error, then 2 into 1 bit error plus 1. So this is the 3 is the minimum distance required. So next with this we will go for Hamming codes. Hamming codes are useful in correcting 1 bit errors. So now parity was detecting 1 bit error. Now with Hamming codes we can correct 1 bit error. So we will add parity bits at position 2 to the power I. So if we consider, say, I have number. Now in this I will add both parity plus data. So 2 to the power 0 should be parity. 2 to the power 1 should be parity. Then it can be data. Then again 2 to the power 2 should be parity. Then data. D5, D6, D7. Again E8 is parity plus 2 to the power 3. Then it can be data. 2 to the power 9, 2 to the power 10, D11, 12, 13, 14, 15. Say now 16. It will be parity bit. So if we have M parity bits, M is greater than or equal to 2, then if these are used to code n bit data, then 2 to the power m should be greater than m plus n, where n is the code data bits in the code. So these are the where we position the parity bits. Now we will see how to generate the parity bits. So now for example we will take a small number p1, P2 should be parity, then it can be data. Again, this will be in the to the power I position, D5, D6, D7. So now the positional values, it will be 0010, 0011, 0100, 0101, 0110, 0111. So these are the binary coded position. So position in binary. Now here the total number of bits are 7 and we use 4 data bits plus 3 parity bits. So the rate we have useful information 4 upon 7. And now to generate P1, it will be with we will consider the data bits in one's place of position. If 1 is there in the place of in one's place of position. So here one's place it is 1. So D3. Exclusive order with here also one's position it is 1. Exclusive order with D7. And then for D bit we want to generate P2. It will be 1 in 2's place. Okay. So now 3 is also D3 is having that. D5 is not D6 and D7. So D6 and D7. Now for P3, D in 1 in 4's place. So it is 4th place. It is D5, D6, D7. So D5, D6, D7. So in this way we generate the parity bits. Now let's take the one more example. Extending this to say a bigger number. Let me consider 8 bits which are useful. So with addition total 12 bits. So this is the rate. So if I consider till 12 bits, so this bit will be parity, then this will be parity, then D3, P4, D5, D6, D7, P8, D9, D10, D11 and D12. So with the place values 5, 6, 7, 8, 9, 10, 11 and 12. So the parity 1, one's place it should be having 1. So what will be the equation? It will be D3, D5, D7, D9. I think this will cover all the odd places because the one's place is 1. The next is P2. When P2 will be 1? When it is 1 at the 2's place position. So D3, D6, D7, D10 and D11. Similarly for P4, D5, D6, D7 and D12. And for P8, it is D9, D10, D11 and D12. So here we have seen their till place 4. So here it's 8th place. 1 in 8th place. So with this, can we try one example? Error correction. If this is 20, I will take one example. If say this data is 1, this is 0, this is 1, this is 1, 0, 1, 0, 1. Then what will be the parity bits? So P1 will be D3, D5, P7, D9 and D11. So this will be 0. Yes, any doubts? So for the next P2 parity, it is D3 XOR D6. Can you tell what will be the value of P2, P4 and P8? Some same way. I will also solve parallelly. So this will be 1 and this will be. So the coded data is, we have generated the parity, which is 0, 0. Then it is the data bit 1. Then parity 1. And then data and one more parity, which is 0. And then followed by data, it is 0 and 0. These are our parity bits. So in this way, we can generate the parity bits. And to correct one bit parity, the C1 correction code will be, if I consider the same equations above, 3, D7, D9, D11. With this, okay, I will write all the equations first. C2, D3. These are the same parity generation equations. We'll use the same for correction, but with one slight modification. D5, D6, D7, D12, and for C8, it was D9, D10, D11, D12. And now the corresponding parity bit also we will XOR. So P1, P2, P4, and P8. And when we are writing, like which bit is having the error, that correction time, we will do like this. So if this C1, C2, C3, C4 are say 0, 0, 0, 0, then there is no error. Else at one particular position, like whichever is one, we will go like this, and that bit position will have the error. So if we consider that say D7 is having the error, then because of the error, this bit will be 1, this bit will be 1, this will be 1, this will be 0. So while writing, we will write like this. So the bit position in which the error is 0, 1, 1, 1. So at the seventh bit, there is erroneous. So if we flip the bit, we can correct that bit position. So even the parity bit can have the error. So if, for example, say C8, I think this is C8, C4, C2, C1. This is how we will write it. So C8, C4, C2, C1. If it is having like this, like 1 0 0, then this indicates 8th bit position, which is a parity bit position. So that means P8 is having error. So in this way, we will correct the 1 bit error. Any doubts? So, okay. With this, now we will see what will happen if we have 2-bit error. So I want the same equations. No problem. I write it. C1, the same equations, so that we can see how it can detect the 2-bit error. So I will copy this so that we can discuss the same equations. So now, if we say there is a 2-bit error, say D5 and D7 are erroneous. So here also there will be error. Here also there will be error. So because of this, there are 2-bit errors. So So because of 2-bit, the XOR will be like 1 XOR 1, so 0. Here it is only 1, so it is, this will be 1. And here also 2, so this will be the equation. If we write like this, we will be getting 0, 0, 1, 0. So we can deduct the error but not correct. We can detect the 2-bit error but not correct. Is it correct for my example? C1 should be 0. Yeah, C2 should be 1. Yes. In the same example, here I am introducing error in D5 and D7. Okay. Let's see. Once D5, D7, so these three equations. So in the same way, if we have 3-bit error, so 3-bit we say that we cannot detect or error also. So if we consider 3-bit flips, say D3, D5 and D6 are having error, then D3, D5, D6, D3, D5, D6 and here. So again this XOR will be 0, this XOR 0, this XOR 0, this XOR 0. So because of this we can't detect all the errors in the 3 bits. So this with this Hamming code we can detect 2-bit error and correct 1-bit error. So next we will solve some questions based on Hamming code. What is the total block length n and the message length k of a Hamming code R is the parity, if R is the parity bit? Can you solve this question? N is the block length, L is the message length, and R are the parity bits. So for each R greater than or equal to 2, then N will be 2 to the power R minus 1 and the message length K will be 2 to the power R minus 1. This we'll take an example and then see. So if we go till 7 and I start inserting the parity bit, so this should be parity. D5, D6, D7. Then how many are the parity bits? 1, 2, 3 parity bits. So how many are the data bits? 1, 2, 3, 4 data bits. So here n is equal to 2 to the power 3 minus, that is 8 minus 1, so total 7. So we can write up to 7. The message total length is 7. And K, this is the total complete length, that is we call block length. Sorry, not the message length, block length. And K is the message length, which is the 3 will go for parity. And this 2 to the power 3 in complete 2 to the power 3 will go for parity, and 1 already we have covered here. So total 8 minus 3 minus 1, 4. So this will be the answer. So it's like 2 to the power r minus 1 is the complete block length. In that r bits will be taken by parity bits itself. So this will be the formula, and the answer to this question is 2 to the power r minus 1, 2 to the power r minus 1 minus r. So option B. Any doubts? Any questions? Can you try this question? 7,4 Hamming code receives this. Determine the correct code word and the transmitted message. So we have to check whether it is correct or not. So it's given 4, 7. This example we have already seen. Can you try? 7, 4 bits, how many parity bits will be there? In this will be parity. This will be parity 2. This is, you can just, I'll write it bigger. 1, 0, 1, 0, 0, 1, 1. So this will be the parity 1, parity 2, data 3, data 4. No, it is to the power. So parity. Then data, data, and data. So what is C1? For correcting it, we have the equation D3 plus D5 plus D7 exclusive one plus D3 XOR D5 XOR D7 and XOR with that corresponding parity bit. And C2 is D3 XOR D6 XOR D7 XOR P2. And C3 is D5 XOR D6 XOR D7 XOR P4. So with this, can you tell the answer? Can you try? What will be the value of C1, C2, C3? What is D2, D3 here? D5, D7 and the parity P1 and D3, D6, D7 and the parity P2, D5, D6 and D7 and parity P4. So what will be the values? This will be 1, this will be 1, this will be 0. So we'll write in this way. So C3, C2, C1 will be 0, 1, 1. So there is an error in this bit position. So this indicates D3. So D3 is erroneous. Then we have to flip that bit. So this will be the corrected. And the other bits will remain same. So this will be the corrected code. So it will be 1, 4 zeros, 1, 1. This or this. And the error is in 0, 0, 1, 1. Correct answer is option A. Before going to the other code types, any doubts in this Hamming code correcting this? Is this question clear? So next we will go to XS3 codes. XS3 is a unweighted code. So to the BCD number, say binary, coded decimal, we add 001 to get XS3. Okay. So the BCD numbers will range from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the BCD corresponding BCD values will be all zeros. 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 6, 0, 1, 1, 0. So this will be the BCD values, and the corresponding XS3 value will be add 3 to this, and then same way. So to every digit we are adding 3. 5 will become 8. 6 will become 9, then 10, 11, 12. So you can see these are the valid XS3 numbers. So 001 to 1100 are the valid XS3 numbers. So okay, if we consider an example 5, 3. What is the XS3 representation for this? If you have any questions, you can unmute yourself and ask. And so 53.
Yes, ma'am, I have a doubt, ma'am.
Yes, please.
Ma'am, the last question we have asked to determine the correct code and the transmitted code.
Yes.
Uh, so the so the correct code is the 4 zeros and 1 1. Is it the same code for the transmitted code, ma'am?
Transmitted, this is the code word 0011 is the code word, and bit position 3 is erroneous, so this bit we have to flip. That could have been the transmitted code.
Okay. The transmitted code is the last 1 4 zeros 1 1, isn't it?
Yes, yes, yes.
Okay, ma'am. Thank you, ma'am.
Yes. So for 53, 5 plus 3, excess 3 will be 8. And for 3, 3 plus 3, it will be 6. So this will be the excess 3. So same way, 6.9, if it is in decimal, to represent in BCD, this will be the in the BCD, the same code. 6 plus 3, it is 9, plus 9 plus 3, it is in the XS3 code. So if we want to convert some more codes, say 10 in the decimal, this is also in decimal. Its XS3 equivalent will be 1 will be 4 and 0 will be 3. XS3. And for example 4, 8, 7 from decimal, XS3. 4 plus 3, 7. 8 plus 4 and 7 plus 4 will be excess 3. Same way for say 99. 9 plus 3 and again 9 plus 3. This will be in excess 3. So these are some of the examples converting the decimal to excess 3 code. And now let's perform addition using excess 3 code. So if we, for example, we perform 5 plus 2, these are in decimal values. What will be the equivalent? 7. What will be the excess 3? This will be plus 3, which will be 8, which will be 1, 0, 0, 0. 2 will be 2 plus 3, 5. 5 will be 0, 1, 0, 1. Now let's add this. So this is one excess 3 and this is another excess 3. 1, 0, 1, 1. Now this will be become our excess 6. So what we have to perform is we have to minus 3. So that is when no carry, that time we have to subtract 0, 0, 1, 1. To subtract 0, 0, 1, 1, I can add minus 3. This is plus 3. What is the minus 3? If I go take 2's complement representation, this will be the minus 3. So I have to add 1, 1, 0. So 1 plus 1, 1, 1 plus 1, 3 ones. So this with 1's complements, you can drop this carry and this number. Deal of this will be excess 3. The number will be positive, so we can take this. Or if you want directly subtract, this is equivalent to the subtraction. So 1 minus 1 is 0. Here you can't subtract, so we will borrow. It will be 2. This will be 0. 2 minus 1 will be 1. So this will be 0. This will be 1. So this is the subtraction. So there will be no carry up to all are 1 in excess 6. And this will be, it is 6 times more. So it is 9 in binary and 9 in decimal. And if you want to convert that to excess 3, it is 12. So till here, there won't be any carry. So now, for example, if there is a carry, what we have to do? If we consider an example, 5 plus 7 in decimal. So there will be a carry, so it will be 12 in decimal. So now 5. Okay. This will be 8 and this will be 1, 0. This will be 10. It is 1, 0, 1, 0. Now 0, 1, 0, 0, 1. So there is one carry. So if there is a carry, if carry is produced, instead of subtracting, before we subtracted, now add 3 or 0, 0, 1, 1 to the result. So it will be 1, 0, add 3 to it. So 1, 0, 1, 0. And to this, 1 in excess 3, it is 4. So this will be the value in excess 3. So the decimal equivalent will be, this is 1. 5 minus 3, it is 2. This is the decimal value. So in this way we perform the excess 3 addition. So if we take one more example for excess 3 addition, say 25 plus 57. So it will be 12 carry 1 8 in this. So now this one. I have to write 8. 2 is 5. And then 5 is 8. And 7 will be 10. Now I go from this addition. Okay. So now first 0, 1, 0. This is 0. There is a carry. I will propagate that carry and keep it here. Okay. Now I will complete this work. There is a carry. So I have to add 3 to it. The value will be 1, 0, 1, 1, 0. Okay. Next 1 plus 1, 0. Carry 1, 1. And then 1 and 1. Triple 1. There is no carry. So I have to subtract minus 3. Or I can add 1, 1, 0, 1. So it will be 1, 0. 1 plus 1, 0, 1. And this is 100. 0 plus 1, 0 plus 1, 1 plus 1, triple 1. So this carry we can leave it and the number is positive. So this is the answer. So this is 8, 2 in decimal. So this is the BCD. We have converted to XS3 and then we have performed the addition using XS3 code. So here in this addition, when there is no carry, we have to subtract from 3, or you can add the 2's complement of 3, 1, 1, 0, 1. And if there is a carry, then you have to add 3. Any doubts in this addition? Okay. And XS3 subtractor. So now for subtraction, we have to say we will perform using 9's complement. And then any XS3 number, if you invert the number, you will obtain its 9's complement. That is, if you take 2, what will be the 9's complement for this? 9 minus 2, which is 7. Now, let's go to XS3. 0, 1, 0, 5. This is in XS3. Now, I will invert this number. We will get 1, 0, 1, 0. What is this value? Which is 10 minus 3. This will be in decimal, which is 7. So, you can say just by inverting an XS3 number, we will get a 9's complement. So the number we have to subtract, we will take the 9's complement, and the same way, if there is a carry, we will add 3. If no carry, subtract 3. The same procedure. Okay, if we do one example, then this will be clear. So let's go to some questions. which of the following statement are true? So XS3 is self-complementing, yes, but it is not sequential. It is a sequential code because as you can see, first will be 3, after that it will be sequential 4, 5, 6. So it is a sequential code only. So this is not correct. And the ASCII means American Standard Code for Information Interchange, and it is a standardized code for computer hardware. There are some other codes, but this is a standardized code. So in 7-bit code, that is 128 codes, we have control codes plus some printable characters. So in this, the capital A as the code 1000001 and small a as the code 11000001, and capital B you have the next value 0010, and small letter b 11000010. Same way if we go for C, it will be 11000011, and capital C 14011. So you can see the value of B is 14010 and 110010. So this is correct. XS3 code is 0011 added to binary code, and the allowed range they have given till 4 ones, and we have seen that in our XS3 code it is from 0011 to 1100. So this is not a valid range. Gray code is an unweighted code we have seen, and with unit distance, and we can obtain using reflection method. And binary to gray, gray to binary, we have seen by using XOR gate we can obtain the conversion. So the correct answers, true options are 2, 5, 4 and 5. Option D. So this we will go for XS3 based subtraction. Let's try one example. 984 minus 599. So 984 minus 599 is 583. But if we want XS3, this will be the XS3 values. Now perform in the addition. So first let me take this 599. 5 will be 9, and then next we have to add 3 to make it XS3. So we have to add 0, 0, 1. And we will get 0, 1, 0, 1. 1 1 0 1 0 1 1 0 1 0 1 0 1 1. So this is our excess 3 representation. Now to take 9's complement, we have to invert this. Okay. Now with this, let's go for 984, and this will be equivalent to 400. So you can verify it. 9's complement is, this will be the 9's complement. So this will be 1011 0 the 400 will be represented as 0011 0011 in excess 3. Next, we have to perform the addition. 0 1 1 0 1. So there is no carry. What we have to do when there is no carry? If carry is produced, we have to add. If no carry, we have to subtract. So the thing is, if carry is 1, then add 3, else subtract 3. Correct? So now, is there a carry? No carry. So I have to subtract 3. So here I have to take a borrow. This will become 0. Again, this will be 1. So now again I have to take a borrow. This will be 1 if I take borrow from here. So this will be 1. This will be 1. And here, now 1 plus 1 0. 1 1 1 1 and 1. Again subtract with 0 0 1 1. So this again we need a borrow 2. Borrow 0 0 will become 2. This will become 0. This will be 1 1 0 1. And now this is 1 1 0 1 0 and 1. We have one carry here. Okay. Now let's see. Here we have to add 3 because there is a carry. So this will be 0 1 1 0. Now this carry we have to add here. This is 0 0 0 1 1 1 0 1 0 1 1 0. This is our final answer. If you see this, it is 6, 11 and 8 in excess 3, and this will be 3, 8 and 5 in decimal. Is it clear? So next we will try one more subtraction. Perform the following addition and subtraction using excess 3 codes. So this will be 10, this will be 9, this will be 9, 5 plus 3, 8. This will be in excess 3. 5, 8, 6. 0.12. Now let us try. This is addition. So can you also try this question and share the answer? So first is 5, next is 6, next 8. 8 will be represented as 11, then 9, then 10 plus 5, 2 plus 3, 5. 5 is, and then 8, 6.12. So here there is no number, so I'll just bring this here. Now we will perform the addition. 1, 0, 1, 0. There is a carry. We have to take this carry here. There is a carry. So we have seen if there is a carry, then add 3. So this satisfies it. So we have to add 3, 0, 0, 1. And what will be the answer? 0, 1, 0, 1, 0, 1, 1. So this no end of correction. Okay, this we have added. Next 0, 1, 1, 1, 0, 1, 0. Now there is a carry. We have to add the carry here. And the answer 0, 0, 1, 1. Add with 3. 1, 0, 1, 0. Next 1 plus 1, 0, 1, 0, 0. Again there is a carry. Here again we have to add with 3. 1, 0, 1, 0. It is 0, 0, 0, 0 and 1. So again for this we have to add 3, and this we have already seen 1 plus 3 will be 4. So this will be the correct answer, and here the decimal point or the binary point. So it is 0. So we have two options. So is this addition clear? Any doubts in this XS3 addition? Okay, if no doubt, then we will go for 58 minus the second part of the question, which is 16. So now this will be minus 4 and 9, XS3. This is 8, 11, minus 10, 7. So now 74. This will be the XS3, 10 and 7. Okay. Now to make it minus 4 or 9's complement, just invert this. We have got it. Now let's write 8 and 11. 8 and 11. And then 74. Just 0, 1, 0, 1, 1, 0, 0. Now we have to perform the addition. So it is 1, 1, 0, 0, and there is a carry 1. So if there is a carry, add with 3. 3 plus 3 will be 6. So 0, 1, 1, 1, 0, 6. Next, 1 plus 1, 1, 1, and 1. There is no carry. So we have to subtract with 3 or add with 2's complement. I just perform x's complement. Triple 1 is 1. And this carry will be. Yes, any doubt? So the answer is this is in excess 3. Now minus, if we keep the sign, then we have to invert this 1, 0, 0, 1. So this is also in excess 3. Let's check the option. 1, 0, 1, 0, 0, and this one. So option B is the correct answer. So is this question clear? So we have performed the excess 3 addition and subtraction based question. So the next ALU. So you have seen ALU is a combinational logic circuit. So the correct answer is option A. The next, which of the following gate acts as 1-bit comparator? So here we say A equal to B by the word 1-bit comparator. So can you say which of the option is correct? Which logic gate will act like a 1-bit comparator? Any answers? Equations, you know? Yes, XNOR. Yes, XNOR is the correct answer. So it is A bar B bar plus AB. If we take two numbers, or usually we will take x0 equal to y0, then it is x0 y0 plus x0 bar y0 bar. So the correct answer is XNOR. Option D. The next question. An error correcting code has the following code words. So what is the maximum number of bit error that can be detected or corrected? So we already know d min is equal to b plus 1 will be for detected, and d min is equal to 2b plus 1 for corrected. With this formula, applying this, can you tell what will be the answer? First, what is the d min value? With, if you see this and this, I think we'll be giving the maximum toggle, or we check the distance between this and this. It is almost all the bits are different. So it is 1, 2, 3, 4, 5, 6, 7, 8. And with this also it is 8. So the D min is 8. Now substituting this value, B is equal to D min minus 1. 7 can be deducted, and D min minus D min minus 1 upon 2 is B, which is corrected. So it is 8 minus 1, it is 3.5, which is corrected. So it is 7 and 3.5. Is this question clear? Any doubts? So correct answer is option D. Then next question.
Ma'am, please repeat, ma'am. That's
Yes, yes. The D min, we already know the formula B plus 1. And D min is 2B plus 1 if where B is the number of bits that we can correct, and here B is the number of bits that we can deduct. Okay. So with this, we have to find D min for the given code. The minimum Hamming distance between this number and this number is the number of bit by bit XOR you perform and add it. So you will get 4 1 plus again 4 1. So it is 8. And again, if you perform the bitwise XOR between this number and this number, again you will get 8. So with this we can say D min is 8. So what is B here? D min minus 1 is B is 7. That many bits we can deduct. The error in 7 bits we can deduct if we use this codes. And D min is equal to 2B plus 1. So if I change B will be D min minus 1 by 2. So we can correct 3.5 bits error. Is it clear now? So the next question, perform the addition, XS3 addition 45 plus 57. So again, if there is a carry plus 3 and if there is no carry, minus 3. So let's start this addition only. So 4, 4 plus 3 is 7 and 5 plus 3 is 8 and 7 plus 3 is 10, 5 plus 3 is 8. Okay, so it is 0, 1, 0, 0, there is a carry. I will propagate the carry here and there is a carry. So add with plus 3. 1, 0, 1, 0. Next here 1 plus 1, 0, 1, 1 plus 1, 1 plus 1, again 0, again 1. So if there is a carry 0, 0, 1, 1. So this will be 1, 1, 0, 0. And this 1 will be in excess 3, 4. So you can say it is 4, 3, 5. So if we perform this addition directly, we will get 5 plus 7 is 12 and this is 10. Now excess 3. This will be 5, this will be 3, this will be 4. So we got 4, 3, 5. And the correct answer is option B. B or A or A. Okay. Then next question, which of the following code is used to transfer information to the CPU of a personal computer? So we have already seen that ASCII codes are used in the computer hardware. So it is ASCII is represented as is full form is American Standard Code for Information Interchange. So the correct answer is D. And the next question. In the given circuit of ALU, which of the following correctly represents the min-term expression of Y0, Y1, considering S has MSB? So this equation, this we can write Y0 as AB whole complement and S is 0, so S bar plus, what is the equation when S is 1? A bar B plus AB bar and S. So we can take the S inside. So it is A bar plus B bar. I'm breaking the bar and this I will keep it. Now let's take it inside. A bar S bar plus B bar S bar plus A bar B S plus A B plus A B R S. So it is A bar B bar S bar plus A bar B S bar. Okay, I'm writing this down. A bar S bar as with multiplied with B bar plus B plus to obtain the min terms. Again for A, I will write with A bar B bar S bar plus A B bar S bar plus the given two terms, other two terms, A bar BS plus A B bar S. With this, can you tell what are the min terms? This are 0, 0, 1, 0. And I have written S as LSB. S should be MSB as per the question. So while writing min terms, we will take as 0. It is 0, 1, 0. So it is 1 and this is 0. Okay, 0 two terms. And this is 0, 1, 0, 2. 1, 0, 1, 5. 1, 1, 0, 6 is for Y0. And for Y1, what is the value? A bar, B bar, S bar plus AB, S. So this is 0, 0, 0, 1, 1, 1. So Y1 is summation M of 0, 7. So the correct answer is 1, 2, 1, 0, 1, 2, 5, 6 and 0 and 7. So option C. Is this question clear? So next we will take this question. So first, what is the value of x3, x2, x1, x0? It is 1, 0, 0, 1. What is the value of y3, y2, y1, y0? It is 111, 0. Okay, this will be helpful for us to calculate. Now we have to find the value at this row and at this output of the circuit. So first x0 y0 is 0 1 and 0, so it is 0. x0 y1, x0 y1, it is 1. x1 y0, x1 y0, it is 0. x1 y1, x1 y1, 0. x2 y0, it is 0 and 0. x2 and y1, it is again 0. x3 and y0, 0. x3 and y1, 1. So, is this clear? So we'll have 0, 1 for the first ladder, 0, 0, then 0, 0, then 0, 1, and this 0 will be at m0. With this, now let's perform the addition. 0 plus 1 is 1, carry is 0. Again, all 0, so this is 0, this is 0. 0, 0, 0, 0, 0. This is 1, 0. Okay, now let's change. Slide, I will change the color and otherwise. x0, y2. x0, y2, 1. x1, y2. x1 is 0, so it will be 0 only. x2 is 0. x3 is 1. y2 is 1. Now, 0 plus 1 is 1 and carry 0. All zeros, so 0, 0. 1, 0, so 1, 0. Here also 1, 0. So the next x0 is 1, y3 is also 1. x1 and x3, x1 and y3. x1 is 0, so this output should be 0 only. You can write here itself, right? And x2 is 0, so no problem. x1, y3 is 1. So now again last product, 0 plus 1, 1, 0, 1, 0, 1, 0, 0 plus 1 plus, so this will be the answer. So what is the answer? 0, 1, 1, 2, 3, 4, 1, again 2, 1 and 0. So this is both answers. And this stage output, I have written in green, right? 0, 1, double 0, 1. No, I think I have to write full output. Okay, so this 0, 1, 1, 0, 0, 0, 0, 1. So the correct answer is C. Any doubt in this question? So any doubts still here? So if no questions, then we can complete today's class. Thank you so much.